team to make close connection between heat source and a heat spreader or a heat sink to achieve low interface resistance. And at the end, reliability. You want your thermal interface materials to perform over the years without any huge degradation in thermal properties. Here we have a table with the different TIMS categories. On the top of this list, we have materials that are poor conductors with high thermal resistance, and at the bottom we have excellent conductors. As we can see here, some of the materials that are still very often used in many applications are at the top of the list. Why is that? Why would anyone use any material with such a poor thermal properties? Well, they are cheap and they are still good enough for many applications. But that will change very soon. On this slide, we can see how power usage was changing with different technologies, and switching from 12 nanometers to 7 nanometers will make a huge jump in power usage. New 7 nanometers processors will use almost 1 watt per square millimeter, and more power means more heat, which means that most of the materials that has been used previously will not be adequate for those applications. We will need materials with lower thermal resistance, and metal TIMS would be the best solution for this technology. And the demand for thermal interface materials will exceed 870,000 tons by 2031. Electric vehicles drive future demands of TIMS, and they will be #1 user of TIMS by the end of the 2031. Now, when we know key attributes of good thermal interface materials, let's see how metal TIMS fits there. Metals have high thermal conductivity. Most of them will work without any degradation in their thermal properties over the time. And they have fairly low bond line thickness. The biggest challenge for the most of the metals would be interface resistance. Metals are very stiff, and you would need to apply extremely high pressure to achieve low thermal resistance. For instance, copper has 386 watts per meter Kelvin thermal conductivity, but it can't be used as a thermal interface materials because it's very rigid metal with power cycling compared to some typical phase change material and thermal grease. Thermal resistance for those two materials will grow over the time, and with compressible TIM, it will drop down at the start, and after that it will be pretty stable. With their unique properties, liquid metals are also a very good solution for thermal interface materials. Just like with compressible TIMs, there is no need for any surface preparation for this type of thermal interface materials. They have high thermal conductivity and can achieve very low bond line thickness. On the right side, we can see how thermal resistance will change with the pressure for one indium-based alloy when material is in solid and liquid phases. Because it's the same alloy, thermal conductivity will be the same, but when material is in liquid phase, interface resistance will be very low, which will provide low thermal resistance even with a very low pressure. As we can see in the table below, mixing of metals will lower both melting point and thermal conductivity. Those are high-density, low-viscosity materials. Liquid metals are non-toxic, they don't evaporate, and they can't be inhaled. Another good property of liquid metal TIMs is that thermal resistance doesn't change dramatically with thickness. For some other thermal interface materials like thermal greases, we will see huge increase of thermal resistance with thicker thermal interface material. On this slide, we can see what would be the biggest challenges for liquid metals thermal interface materials. First of all, those materials are electrically conductive, so they must be contained. Gallium is incompatible with some materials, and it's very aggressive to aluminum. On the right side of this slide, we can see aluminum heat sink. Liquid gallium-indium alloy was applied on the top of it, and after that, heat sink was stored for 7 days at 125 Celsius. Visually, interaction between gallium and aluminum looks like corrosion, but it's not. Gallium will go through grain boundaries of aluminum and completely destroy integrity of the heat sink. If you want to use liquid metals and you have some aluminum parts that can get in contact with it, anodized aluminum would be a good solution. Anodized aluminum will not react with gallium. And at the end, we have oxidation. Liquid metals will oxidize very easily, and that can affect their thermal properties. Latest generation of metal TIMs are solid-liquid hybrids. Those are thermal interface materials that combines metals that are solid at room temperature with metals that are liquid at the room temperatures. Adding solid particles to solid-liquid hybrids will improve thermal conductivity, and liquid metals will provide wetting and low interface resistance. Also, solid metals will minimize risk of leaking and improve oxidation behavior. We have two main types of solid-liquid hybrids: hybrid liquid metal base and solid-liquid hybrids created during chip assembly or M2 TIMs. Hybrid liquid metal bases are formed when liquid metals are mixed with the high melting point metals, solid at room temperatures, creating a high viscosity base-to-look material. Liquid part of hybrid liquid metal base will provide low interface resistance and allow those TIMs to have thin bond line thickness. Solid parts will minimize leaking risk and improve oxidation behavior, as we can see on this slide. Recommended processes for high volume production for those materials are dispensing, jetting, and spraying, and for high viscosity hybrid liquid metal base, printing would be more suitable process. Solid-liquid hybrids created during chip assembly or M2 TIMs are a combination of the solid solder preform and liquid metal. Solid solder preform should be made from material that is highly soluble in gallium. Just like with solid-liquid hybrid base, this material will have low interface resistance and high thermal conductivity. Solid solder preform will also form oxidation barrier and minimize chances of liquid metal leaking. And on this slide, we can see how indium will react with gallium-based liquid metal alloy. Gallium will go through the grain boundaries of indium, providing wetting on the surfaces of the solid solder preform. Thanks to solid indium preform, newly formed matrix will have high thermal conductivity, and liquid metal will provide low interface resistance. Solid indium preform will also help keeping liquid metal in place, so none of the material could be squeezed out. This slide will show us outstanding thermal properties of M2 TIMs. On the left side, we can see how thermal resistance will change with the pressure for M2 TIM and one phase change material. Thermal properties of M2 TIM are much better compared to phase change material. We can also see that for M2 TIMs, the thermal resistance doesn't change too much with the pressure. That means that we can have low thermal resistance even with a very low pressure. Just like with liquid metals, thermal resistance of M2 TIMs doesn't change dramatically with thickness. Basically, this combination of solid and liquid metals will have the best properties of each type, solid and liquid metals. On this video, we can see automated process for high volume production of M2 TIMs. Machine used in this video have dual heads. One is used as a jetting head for a liquid metal, and the other one is used as a robotic arm for placing a solid preform. This would be a preferred option for automated process for M2 TIMs, especially if you want to have 2 layers of liquid metal, one on the back of the silicon die and one on the top of the preform. The other option would be a combination of jetting and pick-and-place machine. As I mentioned before, solid part of M2 TIMs should be a metal or alloy that is highly soluble in gallium. In that case, jetting pattern of liquid metal is not too important. The best practice would be to have liquid metal applied close to the center of the silicon die. That will minimize risk of splashing liquid metal during the placement of the solid solder preform. What is important is to control the amount of liquid metal. If we don't have enough liquid metal, we'll have a higher thermal resistance. If we have too much liquid metal, we can have a leakage issues during the assembly process or after. Solid-liquid hybrids won't pump out. Power cycling process 0 to 80 watts with a peak junction temperature of 105 Celsius was applied on M2 TIM. After more than 20,000 cycles, none of material was pumped out and we couldn't see any huge degradation in performance. At the end, we can say that semiconductor devices will continue to increase power usage and additional power will produce more heat. Most of the thermal interface materials currently used in the industry will not be able to achieve that heat dissipation requirements. Metal TIMs, with their outstanding thermal properties, will be more suitable materials for high-performance devices. And special thanks goes to my colleagues who assisted with this project, Andy Mackey, Tim Jensen, and Ben Rolowitz. Thank you.